Hello. In this example we're going to look at the two proportion z-test, testing to see whether there is a significant statistical difference between two observed proportions. This is taken from last year's exam, 2015, question 4. I'll give you a couple of minutes to read it and then I'll walk you through both the technical development of it and how to do it on your calculator. So a couple of minutes, pause the video, make sure you understand the question. Okay, so what are the hypotheses? Do the data provide convincing statistical evidence that taking a low dose aspirin would reduce the chance of developing colon cancer? So the standard thought is that the null hypothesis is that there is no difference. So null hypothesis is that the proportion who later contract colon cancer with aspirin is the same as the proportion of adults similar to the volunteers who take a placebo. So basically there is no difference in the proportions of incidence of later contracting colon cancer. The alternative hypothesis is that using aspirin reduces this, so the proportion of adults who later contract colon cancer using aspirin should be less than the proportion of adults similar to the volunteer group who use a placebo. And it says that we want alpha to be 0.05. Because this is a strict less than rather than different to, this is a one-tailed test, and what we're trying to do is determine all the 5% in the left tail, and the 5% critical value for a standard normal is minus 1.645. Okay, so that's the hypotheses. Now we've got to figure out whether the conditions are well met to actually do the test. So this is a randomized experiment. So can we actually say for sure that the subjects were randomized? Well, it says in the question that they were. Also, technically, proportion is a count. It's a binomial distribution. We have to confirm that NP and N1 minus P are bigger than 10 for both sets of proportions. Looking at the question, using the aspirin data, NP would be 15, which is bigger than 10, and clearly N1 minus P would be the remaining 485. And for the other data we have 26 and 474. Definitely they're all bigger than 10, so that condition is met. Why is that condition there? Well, technically this is a binomial distribution and we're approximating it by a normal, so we need NP and NQ to be big enough so that the entire normal curve does sit well with the approximation, and it does indeed give a good approximation. These conditions go a long way to guaranteeing that the normal distribution is a good approximation to what's going on. Technically, we should also check for large counts population sizes because we're sampling without replacement, but given the numbers involved this isn't an issue because n is 500 for each group means that that really isn't an issue. So all the conditions are well met, so technically the distribution of the observed sample proportion does follow a normal distribution. The observed proportion of adults similar to the volunteer group who later contract colon cancer using aspirin follows a normal distribution with a mean of the true proportion and a variance equal to the true proportion times by 1 minus the true proportion over n, which is 500. Similarly, the observed proportion of those using the placebo who later develop colon cancer follows a normal distribution, and its mean is the true mean for the placebo, and its variance is true proportion for the placebo times by 1 minus the true proportion for the placebo over its n, which was 500. So when we look at the observed difference in the proportions, we have a difference between two normal distributions, so it is itself normal. The mean of this normal distribution will be the difference in the true proportions. And the variance will be the sum of the variances. So the aspirin over 500 plus the placebo proportion over 500. So this is true. We don't know what these numbers are. We don't know what the true proportion of those affected using aspirin and those affected using the placebo are. So we don't actually know what's going on with the variances either. However, based on the null hypothesis, assuming H0 is true, then we're saying that the proportions are actually equal. So we should use the data to try to find the best estimate of the true proportion. Assuming that they are the same, we should therefore combine the data and say that of the 1,000 volunteers who did this study, 41 of them did later contract colon cancer. So it's the 15 plus the 26 over obviously the 500 plus the 500, and this gives us an observed proportion of 0.041, and we should put this as the best estimate for both of these. So assuming H0 is true, the observed difference the observed proportion with aspirin and the observed proportion of placebo, that difference should now follow a normal with a mean equal to 0 and a variance equal to 0.041 times 0.959 over 500 plus 0.041 times 0.959 over 500. And that is what we're going to do for the test. So using our data, the test statistic equals our observed difference minus 0 over that massive standard deviation. So our observed difference is 15 out of 500 minus 26 out of 500 minus 0 over that big square root. 0.041 times 0.959 over 500 twice. And when we do that test, the answer turns out to be minus 1.7542. But what does this actually mean? Well, we can look at the normal tables and say that the probability of getting a z-score further out than minus 1.7542, and we can use our normal tables and we find out that that is 0.04. This of course is the p-value. What we've done is assumed under H0 that the difference really is 0. We're looking at a one-tail test at 5%, and it turns out that cutoff is minus 1.645, and it turns out that our observed Z value is actually there. In the tail, only 4% of the time you would get an observed difference more extreme than that when there should be none. So what does this mean for the conclusion? Well, clearly it's in the critical region, so there is strong evidence to reject H0. We'll deal with the data at the fine detail of that in a minute. We could of course have simply gone straight to the test. So you can go straight to the calculator if you understand what you're doing. So 2 proportion Z test. Enter the data. Count is 15 over 500 and 26 over 500. And then perform the test. Check that you've done the right thing. The hypothesis is less than. And we find that Z value is minus 1.75. And then here's the key things. All these different P's. We have P is 0.03969. P hat 1 is 0.03. P hat 2 is 0.052. And P hat equals 0.041. P hat is the combined pooled proportion. The combined pooled proportion. When we look at the diagram, we again have the same curve as I just produced. Z is minus 1.75, P is 0.0397. In other words, this probability is 4%. The conclusion is, since the p-value is less than the stated significance value, we reject the null hypothesis and conclude that what? Well, we've rejected the null hypothesis, so we reject it in favour of the alternate. The alternate says that the proportion affected by the aspirin is less than the proportion of those using the placebo, but it absolutely needs to be in context. We conclude that the data does give convincing evidence at the 5% level that the proportion of all adults similar to the volunteers who would later develop colon cancer if they had taken a low dose of aspirin every day is lower than the proportion of all adults similar to the volunteer group who later developed colon cancer had they had taken a placebo every day. And it really does have to be that level of detail in the context. Thank you.